Class 12th Chemistry, Alcohols, Phenols and Ethers, and in this video we will discuss about chemical reactions of ethers. Reactions involving cleavage of CO bond in ethers. Ethers are the least reactive of the functional groups. The cleavage of CO bond in ethers takes place under drastic conditions with excess of hydrogen halides. The reaction of dialkyl ether, that is symmetrical ether, gives two alkyl halide molecules. See the reaction. This is ROR. This R and this R both are same. Okay. When react with the HX, this will give RX and ROH. And in excess of HX, this ROH further react with HX, and this OH is also replaced by X, and we will get Rx. In this way, if you write the overall reaction, we will get these two molecules of alkyl halide. Okay. In case of alkyl aryl ethers, they are cleaved at the alkyl oxygen bond. Clear? Alkyl oxygen bond, not aryl oxygen bond. Due to the more stable aryl oxygen bond, the reaction yields phenol and alkyl halide. You can see this is alkyl aryl ether. When this reacts with the HX, this bond is cleaved. Okay, and that's why this H will go to this and X will go to this. We always get the phenol. This will not cleave from this because there is a partial double bond character between this carbon and this oxygen. Now, if we are having unsymmetrical ether like this ROR dash, this R and this R dash both are different, then this will result in the formation of RX and R dash OH. Now, question arises, which alkyl group will form alkyl halide and which will form alcohol? When primary or secondary alkyl groups are present, it is the lower alkyl group that forms alkyl iodide, because in this case reaction is carried out by SN2 mechanism. See, this is CH3O, CH2, CH3. Okay, both the side primary alkyl groups are there. When this react with the HI, then this lower alkyl, in this case lower is this methyl. This will give the iodide, that is we will get methyl iodide, and this ethyl will convert into the ethyl alcohol. Okay, but if one of the alkyl group is a tertiary group, then the halide formed is a tertiary halide, because in that case reaction will proceed through SN1 mechanism. Like this one is, this is primary alkyl group and this is the tertiary alkyl group. Okay, that's why this I of HI will go to this tertiary group and we will get this tertiary iodide, and this CH3 will convert into alcohol, CH3OH. See the mechanism. In the first step, protonation of ether is taking place. This is ether. When this is added with HI, H from this HI will react with this oxygen and this protonated ether. Now in the second step, this I minus will attack, and now this is the SN2 reaction, and as we already discussed in SN2 reaction, one in transition state is formed. Okay, in this case this I minus is making the bond with this CH3 and this CH3 is going away from this oxygen. Okay, and finally you will get CH3I and CH3CH2OH. Okay, so again remember, in case of primary alkyl group is there in ether, I will go to primary alkyl. Okay, and this will result into the formation of alkyl iodide. Now if HI is in excess, then the reaction is carried out at high temperature. The two conditions are there. HI is in excess and reaction is carried out at high temperature. Then this ethanol formed, this reacts with the another molecule of HI and is converted to ethyl iodide, like this one. This is alcohol. When react with this HI, again this protonated alcohol is formed, and this protonated alcohol will react with I minus, and this will convert into ethyl iodide. Okay. But if we are having the tertiary alkyl halide, then step 2 follow the SN1 mechanism. So the halide formed is a tertiary halide. Like in first step, protonated ether is formed, and in this is the second step. In the second step, if one of the tertiary alkyl group is present, then that will convert into tertiary carbocation. Okay, and then in the next step, the tertiary carbocation is attacked by this I minus, and we will get this. I think this concept is clear. This mechanism is clear to you. Now, in case of anisole, anisole means that is a alkyl, we can say that is a methyl phenyl ether. Okay, that is anisole. Methyl phenyl oxonium ion is formed this by the protonation. Methyl phenyl oxonium ion is formed. The bond between OCS3 is weaker. This bond is weaker. Then the bond between OC6H5, that is this bond. Why? Because carbon of phenyl group is sp2 hybridized, and there is a partial double bond character. Okay, this bond having some partial double bond character, that's why it is not easy to break. You can say this is anisole. This will convert into methyl phenyl oxonium ion. Okay, and in the second step, this I minus, now this I minus will attack or will react with this. This bond will broken down, and I minus will go to CS3, and we will get phenol and CS3I. Therefore, the attack by I minus breaks OCS3 bond to form CS3I. Phenols do not react further to give halides because the sp2 hybridized carbon of phenol cannot undergo nucleophilic substitution reaction needed for conversion to the halide. Now this will not further react with the HI. But again, this carbon is sp2 hybridized, and again there is a partial double bond character between this carbon and this oxygen due to resonance. See the one example. Give the major products that are formed by heating each of the following ethers with HI. First one. Now see the structure of this HI. This is smaller group, and this is larger group, and no tertiary group is present. That's why I will go to smaller group. That's why we will get CS3CH2I, and this H will go to this part, and that's why alcohol is this one. Now in the second case, you can see this is the primary group and this is a tertiary. Okay, that's why I will go to tertiary carbon, and we will get this iodoalkane, and H will go to this, and we will get this alcohol. Now see this one. Now this is C6H5 CH2O C6H5. When HI is reacted, which bond will broken down? We already discussed that this oxygen and this carbon, it will not broken down. This bond will broken down. Okay, and that's why H will go to this oxygen and I will go to this carbon, and we will get these products. Clear? Now electrophilic substitution reaction in benzene ring of alkyl aryl ether. As we know, the alkoxy group, that is OR, is ortho-para-directing and activates the aromatic ring towards electrophilic substitution. And this can be easily explained due to this resonance. Okay, you can see this is a negative charge at ortho position, negative charge at para position, and this is at ortho position. That's why alkoxy group is ortho-para-directing. Now see the reaction. This is anisole. Undergo halogenation, and if bromine is there, this is bromination in presence of ethanoic acid. We will get the para-bromoanisole as a major product and ortho-bromoanisole as a minor product. Nitration. Nitrating mixture is H2SO4 and HNO3. We will get 2 nitroanisole as a minor and 4 nitroanisole as a major product. Now Friedel-Crafts reactions. As we know, Friedel-Crafts reactions are two types, alkylation and acylation. First see this alkylation, that is addition of CH3 in the benzene ring. At the introduction of CH3 group in the benzene ring, when this react with the CH3Cl in the presence of anhydrous AlCl3, we will get, now see at the ortho position CH3 is there. This is 2-methoxytoluene. This is a minor, and this is 4-methoxytoluene. This is a major. Now in this case, actually this is a toluene. That's why this is considered as a derivative of toluene. Now this is acetylation. Introduction of CH3CO group in the benzene ring in the presence of anhydrous AlCl3, and its name is ethanoyl chloride. See, at the ortho position, this COCH3 group is present, and in this case, at the para position, this is COCH3 group is there. Now its name is 2-methoxyacetophenone. Actually, this part, this is acetophenone. Okay, and in this case, at the second position, methoxy group is there. That's why this is 2-methoxyacetophenone, and this is 4-methoxyacetophenone as a major product. Okay, thank you. Now this is all about alcohols, phenols, and ethers. Subscribe my channel. In the next video, we'll start the new chapter, aldehydes, ketones, and carboxylic acid.